Alright guys, welcome back to MECH1340. We're going to dive into Chapter 5 here and get into some basics of PLC programming. Remember, we probably already covered some of this since we're already kind of programming our Siemens 1500s and 314s and things like that right now. But this is a good recap, good review of what we've kind of already done. Remember, I have some separate lectures that go over all of our Siemens programming, so a lot of the stuff in this chapter might be more Alan Bradley specific as I get through the lecture, just because remember our book we're using is Alan Bradley based. Alright, so let's just talk about memory organization, just kind of how it stores everything in our systems. So with our PLC, okay, what is it really storing? It's storing our system functions. Okay, it has some reserve space, it has our program that we're usually putting on our SD card, and just some different subroutines that it goes through. Okay, there are some built-in program organization on the microprocessor that's there as well. But it's really keeping track of our output and input image, our status, all right, what bits going on, if we have a timer, a counter, different controls like that. And just where the designated spaces are for all of us to be able to execute that. Okay, so when we talk about our program files, they're in the processor memory. Okay, and that's where we store the ladder logic. Now the program files, they're in the processor memory, but they're on the SD card with what we are programming. Okay, so we can take an SD card out of one PLC, walk over and put it into the other PLC, and everything should work accordingly. So it shouldn't be too big of a deal and that sort of thing. Okay, but that's where they're stored. Okay, so the data is in the processor's memory. Okay, so we don't rewrite the data. So as it's scanning all the inputs and outputs and going through the system, okay, it doesn't store that on the SD card. The SD card, that memory is strictly just for the programming piece. The data is stored internally. Okay. So that's part of the processor's memory. So that's where it's going to store all the IOs, if the sensor's on or off or that sort of thing, as it's executing through the rungs on your program. Okay? And as you can see, and as we've done in some programs, right, it stores it in that table, and you can look at it whenever you want to and how it stores everything generally as a word. Okay? So we've talked about that stuff in previous lectures as well. So if we're talking inputs and outputs, right, generally, all right, if the input's on, okay, that means the switch is closed. So we'll be receiving a 1 for that. If the input's off, all right, we're going to be receiving a 0. So when we've done that on the 870 trainer, that's when we've done our readings and we have 24 volts is on, or we conclude that that's a 1, or 0 volts is off and we concluded that is a 0 when we were just taking readings on the 870 trainer. Okay, so if the program calls for the output to be on, what it does is it switches, right? So it's going to change the corresponding bit on the table. So we're going to go from 0 to 1 based on the data, and we're going to be reading that from the inputs and outputs, or it's going to based on the inputs that it reads, if the input changes, right? So if we have a Hall sensor, right, and the cylinder opens or closes, it's going to change the status of that bit. So based on the status of that bit, all right, it's going to update the output to either turn on or off some sort of indicator or whatever we're running, like a motor or things like that. Okay, so once again, even with the output models, okay, on is 1, off is 0. So true, false, high, low, whatever you want to use as your indicator, they all mean the same thing, right? Because we're dealing in binary. So let's just talk about, we've talked about different types of PLCs. So micro PLCs, they're fixed PLCs. So those might be like our Siemens logos, very small number of IO, our Siemens 1200s, more fixed PLCs. And then even our 1500s, those can be modular, but we use them as fixed PLCs. But if we look at the 315 one that we have in class, okay, that's our modular one. We can see that there's a bunch of different slots in racks in that case, versus just our 314s, those were fixed. Okay, so the original one. So just remember, we're talking about the number of inputs and outputs. That's really what we're talking about when it's fixed or not fixed. It's not fixing that the IO is constantly a 0 or a 1 or that sort of thing. It's just a number of inputs and outputs that are available to us. Okay, we've talked about this before as well. The program scan, what the PLC does as it's going through. All right, it scans through, it reads all the inputs, it analyzes the inputs based on what you've written in ladder logic. It takes those values and goes through the program, and then it adjusts the outputs. It turns things on or off, open or closes, DCVs, using solenoids, all those different things. All right, so it's reading the inputs and controlling the outputs. It's checking any housekeeping things where it has any internal memory that it's got to store. We're going to talk about memory coils and things like that soon too as well. Okay, but remember, it's constantly doing this scan. Okay, microseconds, milliseconds, things like that. It's constantly going through this scan of reading inputs and adjusting outputs, reading inputs, adjusting outputs based on the program cycle that it goes through. Okay, so it does take time, right, to complete a scan, but to you and I, it takes less than a second for this thing to do all of this. Okay, and different PLC controllers have different speeds associated with them as well. All right, but they got to be able to react to relatively instantaneously. Right, we talked about that being in real time. It's got to react very, very, very fast. Okay, but sometimes if a state changes too quickly, all right, the PLC might not be able to actually detect the change. So sometimes that happens. So we saw that, on some FANUC programs where we had it kind of cycle through something, and if we didn't put a delay in the FANUC program, the state changed too quickly, and the FANUC never picked it up, so we had to put a delay in there. Sometimes you need to do that in the PLC as well, because it can react just too fast and skip over what happened. All right, so scan time, right? It's the speed of the processor module, the length of the ladder program, right? If you've got a really long program, yeah, it's going to take a little while to get through all the rungs. And when I say a little while, I'm still talking like milliseconds, not a second or things like that. And, it's going to be based on the type of instructions, whether we're using timers, counters, different things like that that impact, how the program's functioning and things like that. Okay, so the PLC computes the scan each time the end instruction is executed. Okay, so it starts on your first line, goes down, all right, it ends on your last line, and that's a complete scan, how we call it. Okay, so what's it doing, right? We know about all the input devices, we know about all the output devices, and what's really going on in that processor memory is you've put your program on the SD card, and it's constantly going through your program, reading all the I/O, all right, or reading the inputs, going through the program, changing the outputs constantly over and over and over. So how does it work? All right, so when it scans a ladder logic program, your PLC starts it goes from top to bottom, and it goes from left to right, each rung at a time. So it's going to go left to right, top to bottom, and it's going to go all the way down through your entire ladder program, and then it's going to return back to the top. It's just a constant looping program. All right, we kind of learned that with Adrenal boards, just constantly looping the same program, because this PLC is only doing this specific task. It doesn't need to change programs or anything like that. It doesn't have callouts. It doesn't have subroutines when we do this. It's left to right, top to bottom, each rung at a time, and then starts back over at the top. So that's really kind of how it's going through it. All right, now we can do some different PLC programming languages. For us, we are going to strictly do ladder diagrams. All right, it's the easiest one, and it's going to make the most sense to you, and you just kind of logically think. Some people like the function block diagram. That's not too bad. We might mix a little bit of ladder with some function block, because you can throw some function block in there, or there's sequential function charts. Now, we can do text language like VHDL and things like that. We've experienced that in digital electronics, right? You guys had to write some Verilog code. You also had to kind of write some machine code that we did with the Adrenos and things like that. That's more of your structured text type things, or possible list instructions. Okay, so when we step back to those kind of programming tasks, that's what those meant. All right. We did do graphical language, right, when we used multi-sim and we put all of our logic gates in and things like that as well, so that was graphical language. All right, but for us, all right, ladder diagrams, things like that, that's really what we're going to focus on. Okay, so it's the most common and it makes the most sense, and you can go back and forth between different types of vendors, so like Mitsubishi, Allen Bradley, Siemens. Same structure for the most part, all right? You just got some different tagging things, and you got to understand their counters and timers might work a little bit differently between the different types. Okay, but when we look at the difference here, so the drawing at the top is not how it goes into ladder logic. Okay, that's called the hardwired relay control circuit. So that's how it looks in the field. Okay, you have a push button 1, you got control relay 1, we got a limit switch 1, control relay 2. That relates to the ladder program, however, though. Okay, so hardwired versus ladder logic. Hardwired is where we show it with all the symbols for the exact switches and inputs and outputs that are there, versus the ladder logic where we just use, normally open, normally closed contactors to represent all those I/O. Okay, so that you can kind of see the difference between hardwired relay control, and it almost looks like a schematic, right, that you would see in the field and things like that, and then the actual ladder logic program that the PLC is going to go through. Okay, now if we wanted to do like the list instructions that we talked about. So remember I mentioned, there's multiple types of programming languages, and there's the list instruction. So if we look at the hardwire relay control circuit, so that's the same one as before. If we did a list instruction, okay, you would have to write it in terms of ands and ors, and remember nots. So you would have to write the list out, so the push button 1, right, that's the start. And then you have to AND that with control relay 1, right? Those are ANDed. And then we OR that with limit switch 1. And then the next step would what? AND not control relay 2. And then we would have the output would be the solenoid. Okay, so there's a different way of writing the same program using listing. This is using function blocks. Okay, so the equivalent function block diagram. So if we have an AND for ladder logic, we would use the Boolean function block. Okay, if we have an OR, we would use the OR Boolean, and the AND with the NOT. Notice what's the difference? The bubble down at the bottom on the AND Boolean where we're knotting B. Remember the bubble inverts the signal, so that's how we would put the NOT in. So there's just the same way of writing our PLC programs where we can use function block equivalents. So like I said, we're going to stick mainly with ladder logic and everything that we're doing in here. We used to do this on our FPGA boards, all right, when we did something like this, when we used a function block diagram and so on and so forth. We do some of this because we have the Digilent and Xilinx Nexus 4 DDR FPGA, so we do this, and you guys have done some interaction. So you've done something similar to this using a function block diagram output as well when we used LabVIEW to do Verilog. Okay, so you may or may not have taken that course with me, and it's okay. It's not necessarily relative to what we're doing. It's just it relates, so it kind of helps some of you guys that have gone through that before, maybe to be a little bit step ahead. Okay, but what you really need to think about is, if we have a sequential chart, but this one's important, and all right, and we have some of this in the documentation for the 870 trainer when you guys troubleshoot and things like that. But if you think logically and you think in sequence, this one might make more sense to you as you do it. What steps do you want? What action do you need to take? Then we go to the next step. What happens here? That then interaction. So, an example would be like on station 1 of the 870 trainer, where we have the feed cylinder extends. Well, that might be our initial step, right? What action has to happen? Well, when it extends, then what has to happen? Oh, we got to lower the pickup cylinder, and we have to turn on the vacuum. So that might be our action that we're doing, all right? And then once that happens, then we have to retract the feed cylinder, even though that one's automatic. But I'm just kind of throwing it out there. You need to understand things, sequentially, step by step. Structured text, probably the hardest one, potentially. We've done some Verilog, we've done some machine stuff with Arduinos and things like that. And, it gets a little more complicated. You got to know how you are, writing the program, and there's certain commands, and you get into things that are case sensitive, or you forget to leave the semicolon, and that sort of. We've all made those errors, just writing programs using the Arduino boards and things like that. So, structured text programs probably the hardest way to program. Once you get good at it and you got all the commands down, it's really not too big of a deal. But it's much easier for us to do ladder and drop some contactors on, because essentially the program behind the scenes kind of puts it into like a structured text that converts everything to strings and characters and just ones and zeros and that sort of thing. But for us, it's really easy to just drop stuff in a ladder diagram. Just like when we're programming the Fanix, we could write out all this structured text and things like that, but it's much easier for us to just program some points and things like that. It does the work for us. All right, so relay type instructions. So this is really what we're kind of doing. We have a normally open or normally closed contactor, just like you would have a normally open or normally closed relay. All right, and that's really what we're, how it relates. So we use contactors, and then the outputs we use is coils. Okay, and there's a couple different kinds of coils we can use, and I'm going to get through that as we get through the lecture. Okay, but essentially those are the basics of our ladder. All right, so the two kinds of things that we are going to look at when we have these types of relays. All right, so we have a normally open contactor. So what this does is this is an XIC, examine if closed. So we're looking for if it's closed, and we're going to look for a true or a false. This tells us, if the program is working. So examine if closed applies to the normally open contactor. If it's not closed, we will get a 0. So if it's still in its open state. So the example here showing like a push button, right? If the push button is in the open state and we're waiting for it to close, okay, this symbol will remain as 0 and remain de-energized in our program. It's an examine if closed. If it does close, it produces a 1 and becomes true. Then that rung will go to work. Okay? It will energize that portion of the rung. So remember, because there's different scenarios where we have ands and ors and that has to work. But that's really what examine if closed is doing. It's a normally open contactor, and it's false if it's open, and it's true if it's closed. So 0 if it's open, 1 if it closes. So examine if closed. Okay, so that's really what those status means. I just kind of went through that. All right, so let's take a look here. If we look at the next piece, we have examine if open. Examine if open. That applies to a normally closed signal. So you have to ask yourself, it's looking for, does it open, and what makes it true? Okay, what makes it false in this case? So it's examining the bit memory here. So when we take a look at this, a 1 corresponds to a true status. So we're doing what? Examining if open. Okay, but with this case, it's already closed. So it's going to stay closed, and it will interpret false when the bit is 1, and the ring will not allow. Okay, so does that really... This might be the one that's a little bit more confusing when we talk about these. Just because it seems a little bit backwards when you're doing the examine if open status. Because right now, if it's normally closed, like it is, and everything's operational, okay, it will be allowing it to go through the rung, okay? But in our case, when we're doing examine if closed, a 0 corresponds to an off condition, okay? So what we're really examine if open. Sorry, I misspoke there. It's examine if open. So 0 corresponds to an off condition. So is it open? 0 is interpreted as true. 1 is interpreted as false, right? Because it's a normally closed contactor, so you have to think kind of in the opposite state. So it's going to be how it's wired versus how it's programmed. And that's where, if we talk about an e-stop is normally wired closed. So you have to think a little bit backwards when you use an e-stop in your program and what kind of contactor that you use. And you have to understand how things are wired as well. So what we're really interpreting, look at this input switch. This input switch here is normally open. Okay? You can just tell by the way it's drawn, the symbol. But we're using a normally closed contactor. So what's going to happen is when this push button goes down, it's going to flip what's happening here on the contactor. Alright, so let's look at the output energize. That's what we're really using as our solenoid coil, or our core output coil, I guess I should say, would be the best term to understand this with. So these relate to all the outputs. So when we want to turn a motor on or turn a light on, this is the output that turns it on. So that would be the output energize. So we turn like a green light on, or a red light on, or an amber light on, or the motor starts. Or we want to start a counter, or we want to start a timer. Those are going to be the outputs that we use. Okay, so based on what we do with our inputs, right, our normally open, normally closed contactors, and our series of ands and ors and things like that, all right, this is really what's going to energize when we go through the program. All right, so if we take a look, just basic program here, we have two inputs ANDed together to produce an output, and that output in this case just turns on a light. So as long as 1.1 and 1.4 are true, the output will turn on. Okay, so as long as both of those limit switches close, we'll get an output that's true, and it turns it on. So remember, 1s are on, or 24s are on, right? 24 volt for us, and 0 turns it off. So just basic instruction. Like I said, even though this is Allen Bradley stuff, this is common to every single ladder logic type proprietary program that you're going to be writing with. You either have normally open, normally closed contactors, and you have an output coil that turns things on or off. Okay, and that's kind of the action of what we call the field device. Okay, a signal present makes the normally open bit 1 true, and a signal absent makes the normally open bit 0 false. Okay, and the reverse is true if we're talking about the normally closed contactors. Okay, so what do we mean by the signal present? All right, the signal present means if we look at the push button A in the upper left hand corner there. Right now, the signal's not present, right? Because the button has not been pushed. So it's making our bit status false. There's a 0 there. Then on the right hand side, when we actually press A, press it down, it changes the bit status to a 1, which is true. So how does that look on our ladder logic program? Okay, so if we look down below on the left hand side, we have two rungs. Okay, on your ladder logic. They're both A. Notice that one is when A is normally open, the other is A is normally closed. Okay, so what's it going to do right there? Well, if A is open, right, there's not going to be an output. But if we make it so it's not A, okay, that's the second rung there. When it's not A, it's going to be on. So notice that it's opposite. So if one is true, the other one has to be false, because it's still the same thing. There's A and then there's not A. So if A is 0 right now, right, because the button hasn't been pushed, that means that not A would be a 1 and be outputting true. Then if we look on the right hand side, see how the status changes? All right, we push button A down. What happened to our normally open contactor? Notice how it's green now? That means it's true. Anytime it has green around it, and you'll see when we monitor programs, that's when it's true. So when that turns true, not A goes to 0 and becomes false, because A actually closed on top, right? And then the not A actually opened and did the opposite. So you need to understand, what really happens. This is a really important part here, this slide, of understanding how signals turn on and off and what their status is. So make sure you study this slide and understand this slide. This is very, very, very fundamental here. Understanding how something turns true and false based on pressing of a button. And remember, the button is just an example. There's other things that we can use, that, you know, different switches and sensors and things like that that are going to change the status. Okay? So, what's the main function of ladder logic? Is we want to be able to control outputs based on what the inputs are telling us. Okay, so if we just look at station 1 on the 870 trainer, right? We don't want the feed cylinder to come down and pick up a part the pickup cylinder to come down and pick up a part unless the feed cylinder has given it a part to pick up, right? It's got to make sense, and it's got to go in order, and it's got to, you know, we're not going to be able to trigger, you know, the vacuum to come on if the pickup cylinder hasn't come down yet, because there's no reason to have the vacuum running. So you got to think, it's got to go in order, it's got to make sense, okay? And based on when the inputs hit certain conditions, that's when we control the outputs. All right, so we just got to think logically, how do you want this system to work? So think back to station 1 on the 870, because that's what you're programming as part of your final, okay, is, you know, what has to happen? Well, the feed cylinder has to send a part in and retract, and then the pickup cylinder has to come down, and the vacuum has to come on, right, to come down and pick up the valve body. Then that has to retract, and then it has to carry it over the linear traverse and set it down onto station 2, come back up, and return back home. You have to write the program that goes in that specific sequence, all right, based on all the inputs and outputs, so that it can go through, all right, and properly, you know, move the part from station 1 to station 2, and then start all over and do the automation. But you have to go in a specific order, and specific things have to happen for the next step to occur. So just think about that as we start doing, you know, our programs and things like that. You're creating the path, all right? And I highly suggest when you guys are writing programs and things like this, that you test them in steps, all right? One step at a time. Just like when we did in like digital electronics, right? You breadboarded, you know, one part of your circuit at a time and made sure that everything works correctly, and then you moved on to the next one. So if there was an error at the next step, you know exactly where you are in your troubleshooting. Do not try to write your program in its entirety and, you know, hope that it's going to work the first time through. Odds are it's not going to work the first time through. Okay, so you got to think about your paths, your rungs, you know, and what makes things happen, whether we're anding, we're oring, and those sort of things. Okay, instruction addressing. Now, what's going to happen in these slides? Okay, this is going to be tied to Alan Bradley's stuff, but I am going to recap the Siemens stuff as we go over this. Okay, so everything's got an address, right? And we've covered this a little bit in some other lectures as well. But you have input addresses and you have output addresses, and then we have analog addresses and things like that. Okay, so when we look at this stuff, okay, each, you know, address goes to what? A slot and a specific bit on a PLC. You know, so if this was the 0 slot, but right here it's showing it as the slot 3. Okay, so that means that there's 3 slots on this PLC, and this is referring to slot 3 bit 12. Okay, now with Siemens, we aren't going to have, we do have different slots. So our inputs are going to be slot 0, slot 1, okay, and slot 2. Those are going to be our inputs on our Siemens. And then our bits are only going to go 0 to 7. So that means we're going to go 0, 0 up to 0, 7. And then we're going to go, you know, 1, 0 up to 1, 7 and 2, 0 up to 2, 7. Okay? And then our outputs, notice the output in this case, they use O here. It's on slot 4, okay? And then it's bit 6. So that's going to be how Alan Bradley addresses this. Siemens, we're going to use Q. All right, we're still going to go slot and then bit. But for us, all the program that we're going to do is going to be Q4 and Q5. Those are our slots. Okay, remember Q's for output in Siemens. So we're going to have slot 4 and slot 5. And those also go 0 through 7 for bits, so they're both 8 bits, right? So we can go 4.0 through 4.7 will be outputs in Siemens, as well as 5.0 through 5.7 will be outputs in Siemens. So it's very important. Every program we write, we need to go in and make sure that we change the I/O every time we set it up. And I've emphasized that in my videos where we set up our PLC and make sure that we are changing the correct input, because it defaults to like 126 and things like that with our 1500s when we first start out using the TIA portal. So it's using slots that we don't even have. So we need to make sure that we are changing our inputs and outputs to start correctly in our program. Alright, so if you don't set your PLC up correctly when you're going to do your program, and you go write your program and you're like, oh, I'm using everything right, I'm using inputs, slots 0, 1, and 2, and I write my program, I'm using the correct outputs. But if you didn't set your PLC up correctly, your program's still not going to run, even though you're writing it the way you want and write it with the right inputs and outputs. Okay, so very, very important. When we, make sure that you have the right address for each thing, and to know what's going to get what address. Now, when we're programming on the, the 870 trainer, those already have predefined addresses to all the predefined inputs and outputs. All right, so the limit switches have a specific address. The solenoid coils have a specific address. So there's a list of those at each station so that you know what you're programming. Alright, so you don't just get to make up an input and an output. It's for a specific component when we actually get on the trainer. So everything's going to have its own unique address. Okay, when we start doing branching instructions, okay, remember from a previous lecture, this is how we OR something. ORing is branching. So A or B will turn on C. Essentially, that's what you're doing. Okay, now what they show at the top here, alright, that's how Siemens will probably look. What's on the bottom is how Allen Bradley might look when we go through this. Okay, but there's different ways to branch. Okay, so ours isn't going to look 100% like this in our Siemens software, but it's still the same concept. We're branching, we're ORing. A and not B turn on D, or C turns on D. So I really want you to think about this, A and not B are ANDed, and then we have the OR C. So we're trying to turn on D, but we're branching. Alright, so there's 2 different ways to turn on D. Alright, either A and B are probably some sort of sensor, and C is like a manual switch, or things like that as you go through it. Okay, and there's different ways to make sure that we can do our output branching. And say we want to turn on multiple things. So you want like A or B to turn on a motor and a light indicator and like something else with it. It can do all that, so you can have multiple outputs sometimes there that you can branch on there. Okay, now we have to understand how we do different paths here. So you have A that turns on C or B that turns on C, but you need to have A and D to turn on E, or B and D to turn on E. Okay, so very, very important there that you understand the paths when we start branching. Okay, and then we can use nested paths, so we don't have to rewrite redundant contactors. Okay, we're going to nest branches. What does that mean to nest something? It's just a branch within a branch, so that we can utilize connecting to a certain contactor. So you don't want to write like contactor A in a program like multiple times. Alright, you don't want to write C in multiple times to make something work. So like right here, alright, if we look at the 2 different places that we could possibly put D here, the correct way would be the way on top, right, where we branch D in. So in this case, we would have A and B and C turn on Y, or we would have A and D and C that turn on Y, or we would have A and E that turn on Y. Notice you don't want to repeat the instruction here. Does it make it so the program doesn't work? No, the program will still work. Alright, but there's no reason, because it will slow the program down. If you put the branch of D, if you nest it correctly, alright, you can utilize it so that you don't have to put unnecessary commands in the ladder logic program. Okay, and then some programs, this is the outbound that we're limited here, so we can have a maximum of 10 contactors, whether they're normally open or normally closed, that can turn on one output coil, and we can have maximum of 7 parallel lines, which means what? 7 branches. 7 different things can OR together, and 10 different things can AND together here. So we can have a total of like 70 things going on that control this one rung. All right, if we have that kind of scenario going on. Hopefully you don't have that much going on that's affecting one output right there. All right, so make sure that we understand how to do the Boolean here. Now, what's going to be wrong in this program is we cannot use vertical contactors in ladder logic. So notice how the C in the very top diagram is vertical. You cannot use that. Everything needs to be done horizontally. So you would have to rewrite that, and there'll probably be some homework problems where you got to correct the program. But notice down below is the corrected program for that and how you would rewrite C. All right, because you have multiple paths that it needs to go through. You can go A and D. All right, you need to be able to go B, C, and D, or you need to be able to go A, C, and E, or B and E. So notice how we've had to change that to 4 different lines to make that correct. But it should make sense from your Boolean equation. If you have your Boolean equation correct, all right, you know that you have those 4 different lines and how to write them out. So you can see how the Boolean relates to the correctly programmed ladder logic that's shown here. Okay, and then if we just correct it, right, where to avoid. It's tough because the way this is connected, you cannot have that path from F. It doesn't work backwards, and I think that's what you have to make sure that you understand. So in the top diagram, see how it's trying to go F to D to B to C to turn on Y? Your program, your ladder logic will not do that. One, right, because it moves what? Left to right, top to bottom. It will never move like up and back to the, from left and then back to the left and then up and then to the right. It just won't work that. You have to make sure that you're consistent with the way ladder logic works. Left to right, top to bottom. It will not retrace and go backwards through a program. It has to go in a specific order. All right, there is no way to return back as you're halfway through the program. Okay, so getting back to internal relay instructions, what we use in the Siemens stuff, internal relay coils means it's specific to the processor and the machine. We use it as a memory coil. It's just like in programming where we need to like keep track of a count of something, right? So when we did the FANUC programming, and you used a register, right? And in that register, you stored how many times you did your program. So if you did your box program like 4 or 5 times, right? Or 5 times, it kept track of how many times that box program went around, and it stored it into a specific register. That's the same thing here. This is an internal memory coil, okay? We just call it a memory coil in Siemens, but it doesn't actually turn on any external it doesn't turn on like a motor. It doesn't turn on a solenoid valve or anything like that. It's strictly stored data that can be used. So what you can do is I can say, all right, I need this condition, this, and I need to store that happened into a memory. So I can take that and store it into a memory coil and then use that memory coil to start other things when that condition is true. So it is only internal to the processor, all right? It doesn't impact any outputs. You're just storing that this condition happened. That's really all it's doing. It's like registers and position registers and things like that we did in the FANUC programming and that sort of thing. We are just storing data. That is it. It is not tied to any specific outputs when we do that. So that's the difference between an internal relay coil. And in Siemens, we call that a memory coil. All right, it stores whatever data there happened into memory. All right, so this is what I was saying before. We can store here that when 1, 2, 3, 4, 5, 6, and 7 are all true, we can store that into internal relay. All right, and then when that happens, we can make sure that 8, 9, 10, 11, and 12 rung true, and we turn on some sort of output. Okay, so what is that? Why is that beneficial? In this case, we needed to AND 12 things together. Well, remember that the PLC limits us to ANDing 10. So you can AND a whole bunch of stuff together, put it into a memory coil, and then AND the rest of the things that you need to AND together using that memory coil. Because it'll store that 1, 2, 3, 4, 5, 6, and 7 were all ANDed together and that it's true. And then you can continue with the rest of the inputs to make the output turn on. So there's where you would use that. Okay, so just programming examine if open, examine if close. I know this stuff kind of seems a little confusing. The examine if open probably is more confusing. The examine if close. All right, but if we go through this here, if we take a look at the hardwired circuit versus the program, all right, and remember it's going to highlight in your program when you're monitoring it what's true and what's false so that you can see. All right, so if we take a look at these two push buttons here, we have push button 1, which is normally open, right? That's why we call it NO. And then we have push button 2, which is normally closed. So that's what the NC stands for. Okay, and we're checking out the examine if closed instruction here. Why are we checking out examine if closed? Because we are using normally open contactors. Notice push button 2 is a normally closed push button, but we don't have to say that it's normally closed on the ladder logic. You can, but you don't have to. Okay, it just depends on what you're using it for. So you got to be really careful here between understanding the difference between how something is wired and how you're programming it. I talked to you about this a little bit earlier with the emergency stop button. The emergency stop button, right, is wired normally closed. Why? Because you want to break the circuit when you hit the stop button, not energize the circuit. So that's why it's normally wired closed through the emergency stop. So when you press the emergency stop, it opens the circuit up. So you just got to be careful here how you go through these. Okay. The normal state of the input device doesn't necessarily matter to the controller. It's just inspecting what's true and what's false. So the contactors need to open or close for it to interpret what's going on. So if we use the examine if open, okay, the push button represented by the user program here. So notice the push button in the field is normally open. Okay, that's what hardwired means. That's how it exists in the field. Versus if we use a normally closed contactor. So it's going to inspect, all right, if what happens. So we're going to use the examine if open instruction here. Why? Because in the ladder logic on the right hand side we have a normally closed contactor. Even though in the field the push button is wired normally open. Okay, so how is this going to happen? So it's going to be rung true when the push button is open and false when the push button is closed. Okay, does that make sense? So because right now if the push button's open and we're saying that it's normally closed contactor, okay, as long as that push button stays open, the state that it's in, it's going to be true. The second we hit the push button, what's going to open? The push button's going to close, but the normally closed contactor is going to open and produces a false condition, which is a 0, so it'll turn off that pilot light. Okay, if that makes sense. So you really just gotta, take out of how something is, kind of in the field, and you got to be able to kind of relate it to, what does it really mean? It really means, do I have this function or not this function? And that's really what you're looking for when you take a look at this. So, the basic breakdown here is if we look at this table here, all right, and we have this, this ladder rung at the top. If we're using examine if closed, so we're using a normally open contactor. If the logic is 0, we get a false. If the logic is 1, we get a true. All right, energizing the coil. If we're using examine if open, if our logic is 0, okay, we get a true condition. If our logic is 1, we get a false condition. So it's opposite of what we use to turn on. So it's like we're using the not command to turn something on. Okay, so just remember that examine if open is going to be opposite of examine if closed. Okay, because if we have logic 0, it's not going to be open, right? So it's true. Or 0 opens it, right? And 1 would keep it closed. All right, so that's why it would be false. Okay, so examine if closed, examine if open, and how we use that to turn on the output coil. Okay. I mean, another way you could look at this is, if we're looking at the examine if open, all right, and our logic is a 1, it's going to keep that normally closed contactor closed, but remember, we're examining if it's open, so it's going to keep it false, but it's going to output the energize coil and keep it on. So logic 1 will still keep that on. Logic 0 will turn it off, if that makes sense. Okay. So just another way when we start, looking at time aspects and things like that, and kind of what goes through. Nothing super, astounding here, but what we're talking about, the time aspect, right? What's that relate to? How often it can repeat the scans of the program, and how often it has to update the tables and the bits and things like that as it's going through and doing and scanning. Alright, and lastly, just real quick, just want to talk about the different modes of operation on the PLC. Because sometimes you're going to be like, oh, I uploaded my program or things like that, but you don't have the PLC in the right mode. Okay, there's a program mode, so you can enter a new program, edit it, update it, upload files, all those different things. The run mode is when we turn the PLC so that it's going to execute what's going on and work with our live equipment. We have a test mode. That's to operate or monitor the program. So we can kind of do run and test at the same time. So what you're going to do is you're going to download your program onto the PLC. And we've probably already done this in class. All right, you're going to download your program to the PLC, and you're going to monitor it at the same time. So you're going to have your program open, and you're going to see what's energized, what's not, and then you're going to use the toggle switches that we programmed to turn on some lights or to turn on your stoplight or things like that, and we're going to go through it. So we're going to have our 8 inputs and our 8 outputs, and we're going to be working on that part of the trainer for a little bit so that we understand how to control I/O and make I/O turn on and off as need be. Okay, and then we have a remote position that allows the PLC to be remotely changed. All right, so we can do that. So when we're connected to an IP address or things like that, it allows us to still, if I want to work from home and update a PLC program or make an adaptation, or if I just want to monitor production, make sure something's, making sure that everything's going correctly, I can do that sort of thing. So, all right, guys. Well, that's the basics of setting up a ladder logic program and those sort of things. Like I said, the best way for us to truly understand this stuff is, when we are sitting down and programming and understanding how to write the program and actually how to make inputs and outputs work when we're doing this programming. So, that's what we're going to spend the most of class on. Like I said, I wanted to get through a lot of the lecture stuff, a lot of the book stuff very quickly, because I really want to spend a lot of time in this class sitting down, programming the PLC, and understanding, how we can change inputs and outputs. And I really want to make sure that we all get, station 1 programmed and that sort of thing. So, if you have any questions, guys, feel free to email me if there's something that we needed to kind of clear up. Go ahead and tell me if we need to do a Zoom or a Teams meeting or something like that. Else, guys, I will see you in class or lab, and have a great day.